In our ShiftExample3Opaque, I have intentionally made the values to shift by opaque to the compiler, so it can't know at compile time how much we're going to shift left, how much we're going to shift right, and how much we're going to shift right again. You can see that A is an unsigned long and B and C are signed longs. So basically we're going to have everything in here. You've seen the core shift types already: shift left logical, shift right logical, and shift right arithmetic. So based on the types, whether it's signed or unsigned, we're going to see the same thing, but no longer are we going to see silly and surly. We're going to see sil, surl, and sirrah. Starting with sil, we've got a shift left logical by register. Now it's a register instead of an immediate. So we're going to take the RS1 and we're going to shift it left by the number of bits specified as a value inside of this register. And when we're dealing with RV32 code, it's going to be shifting by 5 bits, and RV64 code, it's going to shift by 6 bits. But hold on a minute. We can see that this is only a single assembly instruction. It's not a double like we saw with silly. So it's only an RV32I, and I'm claiming that this is RV32I, and it'll behave one way, shifting by 5 bits in 32-bit code, and a different way, shifting by 6 bits in 64-bit code. I seem to have just said that that required 2 different assembly instructions in the context of silly and surly and those shifting by immediates. So let's take a quick digression to see why sil is not a double set of 2 instructions the way silly was. So just to cite where I'm getting this point about the things being moved by 5 bits and 6 bits respectively, here are the pages for the 32-bit description of these shifts and the 64-bit description. Now let's look at the actual encoding. Again, I don't really want to get into encoding early in the class, but sometimes you just gotta to really understand what's going on. So here are the encodings for our 32-bit instructions, and we've got silly and surly here. And down here are the encodings for the 64-bit instructions with silly and surly here. So I would direct your attention to the shamped field here, the shift amount. So the shift amount field for a surly in 32-bit is encoded in only 5 bits, 20, 21, 22, 23, 24. 5 bits. Directing your attention down to the 64-bit version, we can see that it's a little bit wider and includes the bit 25. So 6 bits is used and reserved specifically for the shift amount in the 64-bit. And this is the core reason why we have 2 different instructions. One of them is encoded differently from the other. So based on that logic, if we go ahead and look at the encoding for the ones we're going to learn about right now, the sil, the surl, the sirrah, and we check the RV32I section and the RV64I section, if you look across the line here, you will actually see that these things are encoded exactly the same. So this is the basis of why I'm saying silly, surly, and sray are 2 different instructions in 32-bit versus 64-bit, whereas all the other ones, all the other shifts we're going to learn about are the same instruction encoding. So back to the point of it. Sil is shift left logical by register. So again, we've got a register, and that is going to either be interpreted as 5 bits to shift a 32-bit register or 6 bits to shift a 64-bit register. It is a logical shift we're looking at once again, so you're shifting and you're filling in with zeros. It's a left shift, which means you're filling in the least significant bits as you move from right to left. Looking at a concrete example again, let's assume this is RV64I. So we've got sil, A4, A5, A6. Let's say that A6 is holding this value. We look at the bottom 6 bits because it's RV64I, and the bottom 6 bits are a C, a 12 value. And that's of course because I'm lazy and don't want to change my animations where I showed shifting by 12. So A5 is stabba-dabba-dudes, and shift left logical by 12 means that you get everything shifted over by 12 and the bottom 12 bits filled in with zeros, and you lose the top 12 bits. So it's exactly what you already learned about with silly. It's just instead of an I, you're using a register to find out how many bits to shift by. And that's what I'm saying here on this slide. The sil is just the same thing as silly, but use a register for an n-bit shift instead of an immediate. Next instruction, SIRL, shift right logical by register. And no big surprises here. We've got a register. It's going to be used as the shift amount. It is a shift logical, which means you're always filling in bits with zeros, and it is a shift right, which means you're filling in the most significant bits now as you shift from left to right. Concretely, let's assume A6 once again holds 12 and A5 once again holds stabba-dabba-doods. We are going to shift right logical by 12, which means we shift over and it's always going to be zeros here, and the other bits are going to be moved down by 12. And just like SIRL is like a surly, but using a register instead of an immediate. Okay, final thing, shift right arithmetic by register, exact same logic. So register source 2 is the amount to shift by, whether it's 5 bits for 32 or 6 bits for RV64I, and it's an arithmetic shift now. This is the one that's tricky. It's going to shift the bits, but then whatever the most significant bit is, that's what's going to be filled in. So assume RV64I, A6 once again holds 12, and now we have doobie-doobie-doo, and the most significant bit of that is 1. So if we take this and we shift it down to the right by 12, then we get all ones in the most significant bit, everything else shifted down by 12. So shift it by 12 and spread the most significant bit to the most significant 12 bits because we just did a 12-bit shift. All right, SRA is like SRI or SRAY. It's just not using an immediate. It's shifting based on what the register tells it. Cool. Well, you know what you're going to have to do. You've got to step through the assembly and check your understanding. Again, practice makes perfect. Don't skip a section. You got to step through the assembly.